Hello, my name is Jay, and I'm from Illinois. My research paper is on the analysis of various oblique wing configurations, and I did this with the help of my mentor, Annika. So I started by looking at many types of wing designs, and although there's prototypes of many designs, I noticed that there's not a lot of testing. So first, to find a wing design, I noticed that the sweep was very important. So the sweep angle is when is how the wings are in relative to the body of the airplane. So when there's no sweep, that's when the wing is perpendicular to the wing body. And when there is sweep, like the picture on the bottom, which is actually a delta wing, that is when there's a lot of sweep. So more sweep, basically at high speeds, it creates less drag. It makes it go faster. That's why you see a lot of fighter jets have this feature. But at very low speeds, it can have very poor performance. And actually, it can actually get really shaky. So for my design, I wanted to find one of them that had a combination of both of these. At low speeds, it has very little sweep, but at high speeds, it then morphs into a wing that has a high sweep. So like the image on the top, that is a variable sweep wing. But to morph from not having sweep to a lot of sweep on this wing design, it takes a lot of energy. And that kind of makes it so the efficiencies gained from morphing is not worth it because of the amount of energy it takes to morph. So then that's where I landed on the oblique wing. This design, it rotates on its pivot point, and it's kind of similar to the variable sweep wing. It sweeps back more when the speed increases. So it'll rotate like 30 degrees and then it'll rotate more as the speed gets higher. So although one part of the wing is near the front of the airplane and another half is near the back of the airplane, this wing design is actually very balanced or relatively balanced because the center of lift is very similar to very close to the point of center of gravity. And this design could bring like more efficiencies, and this is good because it can increase the speed, increase the range, and even reduce carbon emissions. So then to test the oblique wing, I used Onshape to do CAD modeling, and I based my models off the NASA 81. And I did three configurations. I did one where there was no rotation. It was at 0 degrees, and then another at 30 degrees, and lastly, another one at 60 degrees. So then this simulation, and then after I did the CAD models, I then moved them into SimScale to run a CFD simulation. So this simulation gives us a detailed idea of the airflow around the airplane while it's in the air. And it's kind of similar to the wind tunnel testing, which actually uses physical prototypes to test it with air flowing through the tunnel. So, and then for my parameters, I kind of made it so at when my design was 0 degrees, I had it so the velocity was lower because at low speeds it flies with no sweep. So then as I increased the angle, the speed also increased with it. Yeah, and then I also used the flow region like around the plane, and I used the incompressible fluid flow analysis. And here are my results. At 0 and 30 degrees, it was very balanced, as we can see from the lift distribution. And then at 60 degrees, although a lot more lift was generated, it had very shaky stability. So, in conclusion, I think that more testing needs to be done to make sure this design is good and it can be used. But I think this design has a lot of potential and it can bring more efficiency to the industry. And this could be used in a wide range of applications. And one of them could be currently could be maybe an unmanned aerial system. So basically, there's no people inside since it's very shaky. With people inside, they could get very uncomfortable. But if it's unmanned, then it could definitely be a possibility. And overall, I think the oblique wing will bring new ideas and it'll inspire even other wing designs. And then also with more research and testing, there will be more confidence to believe in new innovative designs. Thank you.